stream's current bit rate is lower than the recommended bit rate, but I think we'll be okay because I can hear you guys just fine. Okay, we're live now.
All right. Well,
All right.
heck yeah. Well, for people joining us right now, we're going to wait a couple minutes until people start to stabilize and enough people are here because, you know, we can't skip our introductions. Y'all want to know who we are.
Yeah.
But at least in the interim, because I can never seem to shut up, we can talk about some galaxies because that's what we're going to be talking about today. Just some odd galaxies, or as my colleague Anne put it here on the slide, galactic menagerie, which I'm terrible at putting on the accent for, but hey, I didn't live in France. I lived in Uzbekistan. But I'm just going to say a couple words on one of my favorite galaxies, NGC 7331. And I particularly love it because a professor of mine had mentioned it in class in passing. And me and a colleague had then, during a study session, got hyper-fixated on wondering whether this would actually be on a test because it seemed like a peculiar galaxy. It's a spiral with this beautifully slightly warped disk. So when you look at a spider diagram, which is like a topographical map for speed, or the Doppler shift, since we're in space, that's how we measure speed. We use the Doppler shift. You know, you look at it, you see what color it is. That tells you how fast it's going, obviously. And it has a beautiful spider diagram. We're studying it for hours on end until we finally get to office hours. And it turns out she just thought it was a gorgeous galaxy and wanted us to know what it looked like. But it's a fun one, NGC 7331. And I mean, there's plenty of others. I don't really want to give any away. I mean, I'm going to be talking about a couple fun galaxies. My colleagues here are going to be talking about a couple more fun galaxies. I got some supernovae to talk about, or novae. I think that's the biggest qualm in our discussions. Or novae. I forgot about that. However it's pronounced. I know how to spell it. It's just SN because we like abbreviations that are confusing. Well, not confusing for that one, but NGC, I always forget what it stands for. And every galaxy we're talking about today, at least me, is starting with NGC. But got a couple more minutes as we wait for people to go on by.
I know what the N and the C stand for, but not the G.
Oh, what do we got? What's N and C?
I'm pretty sure it's new something catalog.
Could be general.
Oh, yeah, you're probably right. Because I know some globular clusters bear the title NGC, and that confused the heck out of me when I was teaching some people about globular clusters. I kept going, well, why are we looking at galaxies? I know NGC is a galaxy. And the teacher was wrong that day.
It's general. It's the new general catalog.
Well, that's delightfully vague.
That is delightfully vague.
Much like, you know, the Very Large Array, the Very Large Telescope, all those fun names that we're so creative about.
Hey, we are creative.
That's what I always tell people. In astronomy, we're very straightforward about what we name our things. People are like, what is it? It's a star made out of neutrons. It's a neutron star.
Okay, you want to talk about magnitudes then? How bright is something? -10. That is, my goodness, I've never seen something that bright. Or, I can't see past 6. That's way too dim. For anyone who doesn't know, the magnitude scale is how we measure how bright things are. And there's a lot of things in astrophysics that are that way due to historical reasons or legacy reasons. And that's one of them, where the higher you go on the magnitude scale, the dimmer the object is. If memory serves, it was under the idea that 0 could then be the brightest object we would see in the night sky. And the fact that we have then absolute magnitude, which is slightly different, where we put all the stars normalized on a certain distance. It gets confusing pretty fast, but heck, I'm working with code right now where I got to change something to magnitude. So I guess some things really just stick.
And I think it wasn't Hippocrates. It was another astronomer, Hipparchus, who came up with it. And he now numbered all stars from 1 to 6. And we've stuck with it ever since.
Or it's like the naming convention where we use the alphabet, but not in alphabetical order, because why would we do that?
I know the story behind that one too.
Okay, all right. We all have to know.
Because when they organized, when they were first cataloging stars and they were organizing them by spectral type, what they were doing, so the letters of stars we now know that those correspond to temperatures. When people were first looking at these things, they didn't know that. So we call them spectral classes because you see very specific types of spectra. So they were grouping them based on spectra and alphabetizing them in a way that they thought made sense based on, I believe, a hydrogen line or some other lines. And then later, people put together that actually what was going on is we were categorizing by temperature. So A, B, C, D, et cetera, didn't make sense anymore, and we had to reorganize it because what we were actually looking at was temperature. So that's why they are the way they are, and that's why we have O, B, A, F, G, K, M.
I always think OB is overly bright, and that helps remind me it's the bright ones. But I love that story because I sadly always forget the name. But a professor was talking to his students about organizing galaxies, and he was just so frustrated with them that he said, my maid could honestly do a better job than you guys. And he put money where his mouth was, hired his maid to become an astrophysicist, and it turns out we have a lot of current naming conventions based on the work that she did. His maid could, in fact, not only do as well, but a heck of a lot better than they did. And I absolutely love it.
That's a good one.
All right, we're 1 minute past. I think it's about time that we give y'all kind folks what we actually came to talk about today. So we're going to introduce ourselves first. I guess since I'm talking, it makes sense for me to do it right now. For me first, we were going to do an alphabetical order, but oh well. My name's Maxwell Kushel. I am an undergraduate here at the University of Minnesota. I'm currently doing research with Professor here, Pat Kelly, on the Turbo Space Telescope, as well as with the Professor Claudia Scarlotta on some work for the Euclid telescope that will be going up next year. And that's a little bit all about me.
Okay, I guess I'll introduce myself then. I'm Ann Dewar. I'm also a senior here at the University of Minnesota, majoring in physics and astrophysics, and I work with Professor Lucy Fortson on gamma ray astronomy. And Ann Isaacs, go ahead and introduce yourself.
Hi, I'm Ann Isaacs. I am an astrophysics PhD candidate here at the university. I also work with Professor Lucy Fortson on gamma ray astronomy. Specifically right now, I'm looking at some Blazars, which is pretty fun. All right, so I'm going to get us started with the galactic menagerie, which is to say the collection of weird galaxies we see throughout the night sky. But in order to do that, we're going to start with what are normal galaxies. So the first kind of galaxy that we're probably used to is a spiral. This is a very common galaxy shape. It looks like a spiral. So we have this bright bit in the center and then these spiral arms going out. We also sometimes see what's called a bar, which just means that the center is kind of extended. And this is a very common type of galaxy. We live in a barred spiral galaxy. That's what the Milky Way is. So we see a lot of these in the night sky. They're usually on the younger side and they're pretty fun to look at. Another very common type of galaxy is an elliptical. These are a little bit less interesting to look at. They look like big blobs of stars. They tend to be older. You probably noticed the previous pictures were bluer. These are a bit yellower. In astronomy, we can say that that means these ones are older. And they are just the biggest old blobs of stars you've ever seen in your life. And that is a very common galaxy. Again, we see a ton of them. What's fun about this picture is you can see our big old elliptical in the front, and then in the background, you can see another little spiral here, which is pretty neat. And then we're going to talk a little bit about galaxies like these, but just want to cover what we call irregular galaxies. So these are usually small, kind of lumpy galaxies that don't have a defined shape. They're not big and round enough to be ellipticals. They're definitely not spiral shaped. So they're just kind of usually clumps of blue stars, and we often see them orbiting much larger galaxies. So for example, some of the Milky Way satellite galaxies are the Large Magellanic Cloud and the Small Magellanic Cloud, which are irregular galaxies. So that's what galaxies normally look like. That's what we expect from them. Here's something we don't expect. This is called Hoag's object. It's a ring galaxy, and you might think, well, that looks like a spiral galaxy. And you'd be right, except that there's no arms. There's this central bit, there's this ring, but there's nothing connecting the central part to the ring. And that's really weird. We don't really expect to see this. This one specifically is famous because it is such a perfect ring, which we don't always see. So there's a few different theories about how these form, and it's possible that each one might contribute to some ring galaxies. So the first one is that there's an instability that flings out the arms. So in this theory, galaxies spin, they rotate. In the same way that the planets orbit around the sun, everything around in a galaxy orbits around its center. So in this theory, the spiral arms, which are just collections of stars, essentially the inner arms are flung outwards. There's so much rotation going on, they're flung out. And so they run into each other and form this kind of ring. So you can see there's kind of vestiges of that structure here, because we see that there's like a couple of places where the ring seems slightly stronger, right? And right on the inside and right on the outside. And they even look like they might be making a very kind of loose spiral kind of shape. Another possibility is that certain kinds of mergers create ring galaxies. So if you timed it just right, theoretically, a very small galaxy kind of passing right through the middle of a very big galaxy would create the kind of energy needed to essentially create this instability that would fling out the rings. The other possibility is that if you've got some accreting intergalactic medium, so the idea is if the galaxy is sort of stealing material from elsewhere, that again alters its structure in such a way that it could make a ring. So this one on the left, the Cartwheel Galaxy, is believed to be from one of these mergers. So what we think happened here is that there was this central bit and another galaxy passed through that, causing the spiral arms to be essentially flung outwards. So as you can see, there's these kind of spokes stretching out to the ring, hence Cartwheel Galaxy. I'm about to talk about how certain kinds of mergers can create these spokes or these lines. So the idea is that by one galaxy passing right through the middle in just the right place, we could end up with this ring of stars being thrown out. The other theory, accreting intergalactic medium, might be something like this. This galaxy, as you can see, the ring is it's lumpy. It's oblong. That's the word. So the idea might be that if this galaxy was already a spiral and it started like scooping up some material over here, the spiral arms may have gotten pulled out around that material and created this ring instead of just the spiral structure. So those are some cool ring galaxies. Again, they're very rare and there's a few of them, but they're pretty neat to look at. Another kind of really weird galaxy we see are these antenna and tadpole galaxies. So as you can see, there's these kind of two central galaxies and they're throwing off these incredibly long trails of stars. So a galaxy is already pretty big and these tails are, 3, 4, 5 times the size of the galaxy. So that's pretty wild. So this pair is called the antenna galaxies because they look like antennae. Reminds me of the TV aerial when I was very, very little. And we believe these are galaxies in the process of colliding. So a cool thing about galaxies is that they can collide. Gravity means that everything is trying to pull everything else closer to it. So if two galaxies get close enough, gravity will pull them closer and closer and closer until they crash into each other. Some of you may have heard that this is going to happen to the Milky Way and Andromeda, which is maybe a little bit concerning, but don't worry. First of all, it's not going to happen for billions upon billions of years. But second of all, a galaxy colliding with another galaxy doesn't actually mean that the stars are going to crash into each other, because stars are actually very small compared to the vastness of the spaces between them. So when two galaxies collide, what happens isn't really that the stars crash into each other. It's that the gases interact with each other and everything sort of gravitationally accretes or pulls together. So what's happening in these galaxies is that you're getting these gravitational interactions that create what are called tidal tails. So in the same way that we can think of tides on Earth as sort of water being flung out or pulled, the water is sort of pulled by the moon. And we get these bulges where the water is out, and then we get the places where the water stays in, and we end up with tides. It's a very similar process here where the gravity starts pulling, the gravity of the two galaxies and their gravitational interaction starts pulling stars, stretching everything apart. And one interesting fact is that you can tell that these tails are very blue, especially compared to the galaxies, because a lot of what gets pulled into the tidal tails is gas and dust and other things that are needed to form stars. And because there's this gravitational interaction, they're getting smushed together. So these tails are often composed of very new blue stars. So some other merging galaxies, this one is called the Tadpole Galaxy because it looks like a tadpole. And again, you can see that there's something funky going on up here. There's this, you can see sort of a spiral structure, but it's very clear that there's other stuff going on. And then again, it's flinging out this tidal tail of stars that, again, gas and stars, largely blue stars that are brand new and forming. Because as these galaxies interact, they're just throwing stuff out left and right. What's interesting about this one is that the tail seems to be going in one direction. So it's unlike this galaxy pair or the previous ones, the antennae galaxies, where you could see there were two tails, maybe one from each galaxy, because you expect these sorts of things to be a little bit more symmetrical. But this one just has one tidal tail. So we don't understand all of why galaxies merge, all of like the stuff going on when a galaxy merges with another galaxy, because it's such an incredibly complicated process just because there's so darn many things in there. But we do know that when these things happen, we're seeing galaxies merge. And we believe that they don't last very long. We believe that these would be something that only exists for a couple thousand years, which may seem like a long time, but in astronomy, we consider that to be very short, which is probably why we don't see that many of them. They are pretty transient. They're there and gone. So if they lived for a long time, we'd expect to see a lot more of them because they would be a long time over which they exist and we could observe them. But instead, we don't see very many. So we think that these happen just for a little bit. And then the galaxies finish merging and settle down into a nice, normal, probably elliptical shape. So that's part of what's really cool about features like tidal tails and actually ring galaxies too. We believe those might be kind of transient features that don't last very long. We get to see a galaxy in transition. We get to see it at a very special time when it's doing something cool and exciting that we get to observe. Okay, we're going to switch over to Maxwell's screen and move on.
All righty. Thank you very much, Anne. And we were so excited to talk about these. We forgot to mention, if there's any questions at all, we have a designated time for them right after I'm done talking, which sometimes seems like forever, but I assure you it will come. And please just put your questions down in the comments and my other colleague, Anne here, will answer them for you. All right, if anyone's been in Zoom meetings, I'm about to say the cursed words of, I'm going to try to share my screen. Here we are. That seems, well, oh no, you can't see all the nitty gritty behind it. That's rude. Here we are. Okay, so I'm going to be talking about NGC 1052 DF2, which obviously needs no introduction. I mean, we all know about it, but it's past 8 p.m., which personally is almost close to my bedtime, so I'll remind us all what we're looking at here and what's so important about it. So this is another type of elliptical galaxy. And once again, those kind of look like footballs, cigars, or just weirdly shaped soccer balls or anything. What do you want to call it? It's an elliptical galaxy. And the peculiar thing about this one is that it has a very small amount of dark matter. Now let's talk about that. Why is that interesting? Well, in order to go into why that's interesting, let's first mention a tiny little bit about how galactic evolution occurs. How do these things form in the first place? So let's rewind a couple billion years when the universe was much more filled with hot dark matter. That's a weird phrase. What's hot dark matter? How does dark matter have a temperature? Well, in space, we usually use the velocity, or the velocity dispersion, if we're getting fancy with it, to determine our temperature. There's a nice mathematical relation there to help us get the temperature. If you've studied anything about the kinetic theory of gases, it's a very similar idea. So we're in a time in the universe when dark matter is zooming around and it's way too fast to settle down. Now, why do I want it to settle down? Well, in order to form any meaningful structure, it can't be too hot. We need at least a cool enough temperature for normal matter to get together and form the wonderful things of stars and spiral arms and galaxies that we know and love today. So throughout the evolution of the universe, dark matter cools down, but it turns out because it only interacts with gravity, it's absolutely horrendously terrible at cooling down. And so only small blobs cool down at a certain time. We call these dark matter halos. And to any Xbox fans out there, I profusely apologize. They're not nearly as cool looking as those halos. They truly do look more like blobs, but halo sounds a little cooler than blob, so we're going to use halo. So these halos cool down, and that allows for a galaxy to form inside. And that's an important process because it means that galaxies are surrounded by and contain a large amount of dark matter. And this is actually how they were able to first theorize dark matter existed, by looking at the relationship of the velocity for the Milky Way compared to the distance from the center. One would expect the velocity to slowly go down, gravity's going down, you know, we can't go as fast. But no, it ended up plateauing. And so that was one of the first things that led us to believe dark matter exists. So all right, I've ranted enough about dark matter. Why is 1052 DF2 so important and so fun? Well, scientists were looking at this galaxy, and by observing the Doppler shifts of the velocity, or the fancy way to say it, the color, they were able to find that this galaxy doesn't have enough dark matter. Heck, some of them were even bold enough to claim that it has little to no dark matter. Now, you might think, oh, okay, it's just a peculiar galaxy. But remember, I introduced this as we have to have dark matter cooling down first to then form the galaxy. So if the dark matter didn't cool down, if it's not there, how did this form? This through a massive break in this system. We had no idea how to solve this, and it's currently still a little under debate. Heck, that's why I'm talking about it now. But why is that so important? You're like, okay, so this one might be peculiar. It might have evolved a little differently. That's fun. Some think it could have been a merger, a slight near miss with another galaxy, and the gravity of the other one is slowly robbing it of its dark matter. But the real fun thing about this, the real nice thing about this galaxy is it honestly helps us prove that dark matter has to be some other thing than matter. Because, and I use prove very loosely, please don't get angry at me, any professors watching, but because if this thing has little to no dark matter, yet and exhibits the relationship that we think it should, then it's evidence that dark matter isn't just some other consequence of gravity. Some people think that dark matter is just a weird consequence of relativity or gravity that we're just not smart enough to figure out yet. And heck, yeah, I could probably go for learning a little bit more about science, but oh dear, I've gone to the next one. But that's just not a satisfying answer, that we're just not done. So to end this little talk about this galaxy, it's a little disappointing because we still don't really know about it. I've subtitled it Confusion on Diffusion because I just love a play on words, but also because it is a little confusing at how far away this galaxy is. And I was recently reading about how some scientists report that it's actually much, much closer than people originally thought. And so that means that our measurements are completely off, and it could very much have dark matter content in it. But DF4, another one found near this one, has also been found to have little to no dark matter. So heck, the search for what could possibly have caused this still continues to this day. And that's one of the fun things about this galaxy. It's not always what's there that's confusing. Sometimes it's what's gone. So, all right, you had a sneak peek of NGC 4622. Let's talk about it. And naturally, like the other one, it needs no introduction, but I'll give one anyway because they're paying me to do it. And I love to. So we're looking at this. It's a spiral galaxy, and you got to believe me, it's a spiral because it does not look like it's got some normal arms. But heck, this is galactic menagerie. This is why we're talking about it. It's called a leading arm spiral. And I have to explain just a little bit about spiral structure in order to let y'all know the fanciness and beauty of why this is so strange. So, as my colleague Anne mentioned, spiral galaxies have a bulge in the center, sometimes a bar. This one doesn't have it, so we'll just swipe that under the rug. Let's not talk about that. It's got a bulge and a disk. Those are the two major physical features of a spiral galaxy. Now you might be going, hey, fancy science man on the internet, I can see spiral arms. How is that not a physical thing? Okay, well then look at the ocean and tell me waves are not an overdensity, but rather a physical thing. I feel that calling them an overdensity is a little bit more accurate, wouldn't you say? And now you have disproved yourself. So spiral arms are not some physical thing, they're simply an overdensity in the disk. The reason why we see them so bright and so beautifully is because they're an overdensity. They happen to be regions of major star formation. So it's stars. It's going to be bright. That's some stars. I feel like you don't need me to tell you that. So what's peculiar about this? Well, the disk in a spiral galaxy, one assumes to have a relatively uniform rotation. I mean uniform in direction. So we're either going clockwise or counterclockwise. And the spiral arms tend to follow that same structure. Think of taking a string and just spinning it in a circle. The way those arms form on the string is how we would expect to see the arms form in the relative motion of the galaxy. And so just to kind of show you a little bit of a more normal spiral, this one isn't too normal. It's got a bar in it. I know I said I'd sweep it under the rug. I'm sorry, I'm bringing it up again, but that's just because it's got these two beautiful arms. So as you can see, we're spinning in most likely a counterclockwise way. I say most likely because I found this image and I wasn't able to find too many reports on it. So I say most likely, but that's how a galaxy's arms are typically supposed to form relative to how the disk is actually moving. So what's up with this one? Why do we have leading spiral arms? So, okay, let's dissect this a little bit. Let's go into it. All right, so if we look at these outer arms, these end up being the ones that are actually leading. So they suggest that our galaxy is going in a counterclockwise motion. But thanks to good old Doppler and his shift, we know that it's actually going in a clockwise direction. And that's very peculiar. See, the science behind spiral arms, I'm not going to lie to you, is quite misunderstood, maybe much like all of us. And it's originally thought that it's just an instability that originally causes these arms to form. But most theories that at least I've encountered all stand on that they are held and supported by the rotation of the disk. Yet here we have something that is seemingly, at least visually, rotating in the opposite direction that it actually is. And you can see in these tiny arms on the center, it's starting to correct itself where the velocity has a little bit more power to it, a little more oomph or gusto to it. But the outside, where the velocity is still not as dominant, a peculiar term to use for velocity, but still not as dominant, we see the spiral arms are still only leading. Now, I wish I had a fun explanation for exactly why this galaxy formed in the way it does, but as I said, spiral arms, heck, we barely know anything about them, and we live in one galaxy with them. And for this one, it's no exception. My personal favorite theory for it is we had a merger of another face-on spiral, where two spirals collided like that, and the preservation of angular momentum, shout out to Noether, one of the greatest mathematicians of all time, you can at me on that, that conservation of angular momentum is what caused those spiral arms to still be leading. So people theorize that this isn't something that happened from birth, if you will, for this galaxy, but rather something it picked up along the way. So, all right. Now, I joked about the other ones that you might know what I'm talking about, and I assure you it was a joke. I don't remember those names even now when I just presented them. But this one, if you know anything about a supernova, you should know about 1987A. And if you don't, I just gave you something to Google. So 1987A, a supernova that occurred in one of the Magellanic Clouds, the Large Magellanic Cloud, I do believe. And it was a supernova, the first one to occur in the year 1987. So why is it important? Well, I said it was in the Large Magellanic Cloud. If you know anything about our little local group here, you know that that's really close to the Milky Way. Heck, it's one of the closest galaxies you can get. And that makes this supernova important because you could see it with the bare eye in the sky. That's fascinating. It was so bright and so close. So, okay, let's talk about it. Why am I bringing up this is Galactic Oddities or Galactic Menagerie? What's so important about it? What's so odd? Okay, let's talk about a supernova here real quick. So a supernova, and once again, professors, I apologize. I am trying to be brief here. A supernova is really a massive explosion from a massive star. Think violet supergiant. Now, the core of this star happens to create this shock wave that will then blow out all the other enveloping layers. Now you might be a little smart there because heck, you're watching this video and you might be thinking to yourself, well, I know Newton's laws. If I have a nice shock wave out, shouldn't I have a shock wave in? And you'd be right in thinking that. And it's theorized that supernovae will create some of the densest objects known to humankind. As mentioned previously, a neutron star is possibly one of the outcomes, and a black hole is possibly another. So to be brief and simple, we'll say, all right, if I see a supernova happen, I know one of two things is going to occur. We're going to have a beautiful neutron star, or we're going to have an equally beautiful black hole. And a neutron star is a star made up entirely of neutrons. It's so dense that the only thing that could remain quantum mechanically, yes, I just wanted to say that, is the neutrons. And because of this, it ends up emitting a reasonable amount of X-ray radiation. And that's one of the ways that we are able to detect these supernovae. You might hear pulsars. The reason why they're pulsing is they're pulsing in this X-ray. And so if we were looking at this, we would expect this beautifully gorgeous X-ray signature, or at least something absorbed and re-emitted akin to the X-ray. Or if it's a black hole, which I feel needs no introduction, but I'm here, so I'll give one, is a hyperdense object that is so powerful in its gravity that at a certain distance, not even light can escape. So one of these two things occurs when a supernova explodes. And in 1987, they had the opportunity to look at this for hours, for days, for weeks, for years, to try to figure out what it is. And that was the odd thing about it. It was one of two things, and it was neither. It stumped physicists for over 30 years. And now you might immediately think, well, heck, how could they not know what's in it? You can look at it. Oh, come on. It's a 3D explosion. I can't look through that shock wave. I need to use some fancy science trickery to look through that shock wave. And my trickery was not enough, not nearly enough to figure out what was going on in this. And it turns out after this big galactic goose chase to figure out what is in this, when I was studying astrophysics, Professor Bob Gertz told me about this supernova and said, we have no idea what's in it. You can go and study it yourself. Well, it turns out someone beat me to the punch, and they found that it is most likely a neutron star inside this explosion. And before I pass it on to the Q&A, I think there's one more thing that's worth mentioning in this, which is that little ring that you see there. There's this beautiful video that was released. I wanted to show it here, but video and live streaming, we all know how that works. So you can find it yourself. There's a beautiful video on how that ring propagated and how it changed over time. Because what that is the dust absorbing and re-emitting the radiation. And I thought that was a quite neat little thing to say about it. So, all right, that's everything about supernovae. And now I do believe it's time for us to start answering some of your questions.
Okay, so we have one from earlier on in the talk. Daniel Burbank asks, are these cool colliding galaxy shapes possible to simulate with a computer program?
I can answer this one. One of my really good friends actually did his senior thesis on using n-body simulations and fluid dynamics to model galactic mergers. That was a lot. So an n-body simulation means that you basically model the galaxy as a collection of stars, and then at every step in the simulation, you compute the force of each star on each other star. very computationally heavy. The more objects you get, it gets bigger and bigger and harder to work with. And in fluid dynamics, you model the galaxy as a kind of fluid made of stars, which sounds really weird, but actually does make a lot of sense. And basically, the gist of the presentation of his senior thesis was, well, these are both pretty cool and very promising, but we just can't get up to the level of precision yet needed to model real mergers. So n-body simulations are generally more popular, but basically we're still learning a lot about how this works, and we're also still building the computers powerful enough to make those simulations.
Okay, I don't want to butt in too much, but I actually have a really fun fact for this one. So the Eagle simulation is a common one if you want something Googleable. That's all caps Eagle. And I was reading a paper last year about the merger history of the Milky Way. I highly recommend it. And it turns out that the Milky Way most likely went through multiple mergers in the past. And the most recent of which, and this is why I'm mentioning it, was called the Kraken. And I just thought that was really neat. But yes, they in fact did use n-body simulations to try to get it. But as my colleague said, we're still getting close. We are bound by the power of computers these days.
I've run things on a supercomputer, and I gotta say, when you run something on a supercomputer and it takes an hour or 2 hours, you start to get a little nervous about it. So I can promise you, there are computational limits.
There aren't any more questions in the chat right now. I don't know if you guys have something else maybe you'd like to talk about in the meantime.
You want to check the live stream? That's where I sent all my the YouTube. That's where I sent all my students.
Yeah, I only saw
the
n-body question.
Well, that's quite all right. We can move on.
Trying to think of other cool galactic facts I know.
Oh, yeah, another question. Yep.
I was going to mention galactic cannibalism, which has got to be one of my favorite things, and refers to during the collision of two galaxies when one supermassive black hole gobbles up the other supermassive black hole, which is just such a great name and such a dramatic phenomenon. That's my favorite part of a galactic merger.
Okay, so Thomas Walsh asks, will quantum computers be able to solve these simulations better than regular supercomputers?
Presumably. When we get them up and running, I mean, that's kind of the point.
Oh,
well, like a quantum computer can factor a large prime, and is it n log n time?
That I don't know. But quantum computing, yes, it's something that is very interesting because, yeah, it could very much help solve for this. One of the problems with astrophysics just in general is that you're dealing with something that is parsecs on scale or megaparsecs on scale sometimes. And it's
a parsec is about 3 light years.
Thank you, Anne. And it's determined by the relationships on things sometimes on the angstrom scale, meaning the atomic scale. So it's a difficult thing to simulate galaxies or even just stars. You'd think it'd be a little easier because you have like the convection zone in a star, a very difficult thing to simulate that relies on the quantum mechanics of those objects. I mean, it's fusion is how stars are powered. You can't ignore the quantum mechanical effects. So I think that, yeah, a quantum computer would definitely help us figure it out.
Fingers crossed anyways.
I'm sure a couple professors at the U would agree with you. I believe it is Krau and Pribiak, I hope I'm pronouncing the last names correctly, are currently working on quantum computing. It's one of the reasons I'm proud to be going to the University of Minnesota. But do we have any other questions? All righty then. Let me think, since y'all are obviously entirely captivated that you just want some more information on space. And I feel we must then deliver. I mean, it is only 34 minutes into it. There's gotta be more. So let's think about that. Let's think here.
So also give me a moment to get our activity ready.
Thank you there, the other Anne. let's think. So one of my favorite topics is active galactic nuclei. And it's one of my favorite topics, not because I know a lot about it. I know little to nothing about it. But what I do know is this analogy that I have, which is literally just a donut with a spear thrown through it. And I refuse to accept that anything is better. And here's why. So active galactic nuclei are the massive black holes at the center of galaxies. And it's a little more beyond that. It's not just a massive black hole. There's this obscuring torus, which torus is, in my opinion, a fancy word for a donut. Please don't get angry at me, mathematicians. And as Anne was mentioning, studying blazars, well, AGN were such a peculiar object when they were first discovered because, and here, y'all can see my pretty face now when I'm talking. So AGN were a peculiar thing when they were first discovered because at first they thought it was all these different objects that, like quasars, blazars, quasars, RQSO, a bunch of different ideas for what these objects could be. And they thought they were all these different things. And it turns out it was just a bunch of different ways of looking at one super complicated object that is an AGN. And so the basic structure is this obscuring torus, this big donut of gas and objects, as well as this accretion disk that helps sustain the black hole, if you will, or at least a lot of the radiation that we would be receiving. And then out the two ends are blazars, which, and correct me if I'm mistaken, are relativistic, well, are going so fast that they are relativistic. And when looking at them, this was a peculiar thing. It seemed that when we were looking at two blazars, and I do wish I had a name for them, but we were looking at two blazars, they were going faster than the speed of light compared to each other. And that's a big no-no. We cannot do that. Faster than the speed of light is not okay, because then Einstein starts rolling over in his grave, and that's not okay. And it turned out that due to the fact that these are emitting straight at you and the geometry of the system, it was really just two objects moving at a relatively normal speed compared to each other. But geometry was playing tricks on us. So little fun fact for people, if you're struggling with some geometry, don't worry. It gets relativistic later on, and that's super fun. All right, I'm being told that we have a couple more questions.
Okay, so C. Sampson from Minnesota asks us if we expect galactic collisions to increase or decrease as the universe ages.
Well, I mean, before there's galaxies, you've got no galactic collisions, but with the Hubble expansion,
I believe
this is a fascinating question.
Yeah, I believe that we somewhat expect them. Actually, isn't that still kind of up in the air?
I believe that would be, yeah, that seems like one of those things that we wouldn't have figured out yet.
Yeah.
For those of you who aren't aware, the Hubble expansion refers to the fact that everything in the universe is moving away from everything else. And if you've ever heard of dark energy, that's kind of where that idea comes from. It's something that's driving this expansion. And gravity is what pulls things together. So while the universe is expanding, it's also true that there's still, galaxies are forming and mergers that got started a long time ago. We were gravitationally bound up with Andromeda that we're going to crash into a long time ago. So mergers that got started are going to happen anyway. But yeah, I don't know.
Now, if you believe that the cosmological constant is a little less so of a constant, I know there's one theory of the big tear, where basically if the energy density of this constant, and the idea is that the energy density is constant, and if the energy density of this is in fact not constant and growing with time, then eventually it will overcome the energy density of galaxies. And so one could, I guess, say that it's not like we're going to see more mergers. We're going to see galaxies ripped apart by the energy of space-time itself, which if you're a sci-fi writer, please use that. It's beautiful.
The Big Rip is a wild one. Actually, if you saw our cosmology presentation last term, you may have heard about it.
So it's the Big Bounce. Okay, we have one more. Does anyone use AI techniques with presenting photos and redshift plots?
Well, I do know of some, well, we're about to get into a cool experiment with crowdsourcing that I believe was compared to some AIs. We don't really call them AIs, though. We call them, we will write code that looks for certain patterns in data. So things like you'll write some code, you'll give it some test data and say like, okay, this is what you want to find. And you feed in the data and the computer spits out an answer.
An alternative name is machine learning.
Machine learning, that's probably a better one. Yeah, I think we do some of that. I remember it was in that paper we read on some of us who were in the cosmology and lensing course last term. We talked about machine learning in that particular domain in lensing galaxies. I'm sure it's being done.
Mm-hmm. Yeah, that paper that you mentioned there, it found that machine learning could potentially not be as good as crowdsourcing, or at least comparable to. So if anyone's at home, please feel free to go on your internet and go to Zooniverse, because you're going to be better than a machine.
I mean, that's what we're about to do. I would like to share one quick last note on this, which is I understand from my computer science friends that one of the trickiest things to get a machine to do is to understand a photo or an image. And so, you can give it a bunch of numbers and it says, yeah, I know what to do with this. If you ask a computer to look at a photo, that's just really hard for them for a variety of reasons. So using your human eyeballs and your human intuition, you get to can actually work even better. Should I start sharing my screen for Zooniverse then?
Yep, and I just sent the link in the chat. If you didn't get that, you can just search up Galaxy Zoo Zooniverse, and it'll probably be the first link on Google.
Excuse me. Yeah, so this is the Zooniverse. So what we do here is classify galaxies. Yeah, you can sign in if you want. So the first step is a galaxy smooth or rounded? Smooth and rounded, or does it have a disk? And if it, then you can also put it to star or an artifact, which means it just looks weird. So I think we would all say this is a smooth one. We don't see much of a disk here. Then hit next. Then it asks you what shape it is. So the completely round, like a circle, kind of oblong, or cigar shaped. So Maxwell and I were talking about how these are kind of the options for an elliptical galaxy, and we have successfully classified this as an elliptical galaxy. So I'm going to go with cigar shaped. And then we can say, is the galaxy merging or disturbed? So we just saw some really cool merging galaxies, and you'll see that sometimes, but you also see some more minor mergers and disturbances. So like Maxwell was talking about a possible near-miss merger where a galaxy just kind of, galaxies pass very close, one of them maybe steals some stars. So a minor disturbance like this where it's just a little bit off, or a major disturbance like perhaps it's got a whole little tail coming off of it. In this case, I'm going to go with none. This looks like a pretty unmerged galaxy. And then these are some of the rare features we talked about. We talked about rings, we talked about irregulars, we talked about a couple other things. A dust lane, which is just a dark line over the galaxy full of galactic dust, which is just a bunch of particles that absorb light. I'm delighted to learn that galaxies can be dusty because that means I can be allergic to them. I'm allergic to dust. It's everywhere. Overlapping, of course, stuff sometimes happens to be in the same place on the sky, and a lens or an arc would be gravitational lensing is a whole nother topic, but it is the idea that very heavy objects bend space-time like a lens. So we'll see sometimes these cool arcs on the edge of a galaxy, and something else, of course, if it looks weird in some other way. I don't know about you guys, but this one looks pretty normal to me.
I'd say pretty normal.
Yep. So I can hit done, and I've made a contribution. So do we want to do a few more of these, or I'm kind of down to do a few more if you guys are.
Let's show them a few more. It's always fun to look at galaxies.
Yeah, I would love to. I'd love it if people could put in their input in the chat, because I think that's a lot of fun. Okay, so this one, smooth, disk, or artifact?
I'm putting my vote down on disk. That looks spirally to me.
It does. It's kind of interesting because it looks like there's like different rings of brightness, but not necessarily a spiral structure.
possibly, and I really just want to use this term, an oblate spheroid.
We didn't talk about this, but there is a galaxy type that is considered sort of between an elliptical and a spiral. So do we have answers?
Nothing in the chat.
Well, I think I'll call it a disk for now. Okay.
Okay, we actually just got a question
Wonderful.
referring to the classification of cigar-shaped. So could a cigar-shaped galaxy be a round disk or ellipse seen on edge? And can you tell by looking at the redshifts on the edges of the galaxies?
It absolutely could be, which is part of, we have actually just pulled up to the perfect question for this. Like, could this be a disk viewed edge on? Because if you've got a flat disk and you view it from the side, it'll look like, it just looks like a line. Sort of, if you hold a CD up like that. Oh man, nobody uses CDs anymore.
A coaster?
A coaster? I don't know. I don't have anything flat around me. Yeah, I got my my Enterprise car share card. But my point is, yes, this is absolutely a thing. It is a problem. I believe that one way would be probably a Doppler shift, but elliptical galaxies also do have some rotation to them. I'm not sure. I know that if you sometimes you can see a visible bulge. So you see this flat line and then like a visible bulge where the center of the galaxy is. Sometimes I think you're just kind of looking at it being like, well, it looks kind of blue, so probably a spiral.
Shout out to spider diagrams, basically a topographical map for Doppler shift. And exactly as you were saying, that's how we can partly use it. And fun fact about ellipticals, yes, they do have orbits. Yes, they can be mistaken or confusing. None of them have closed orbits. Not a single object in that whole darn thing is a closed orbit. It's chaos, but beautiful chaos. Yeah,
since an elliptical has a certain symmetry to it, you don't expect everything to be rotating in one plane. It's going to be all over the place. So we're going to say this is not an edge-on disk while we're on the topic. Okay, so now it's going to ask us if we see a bar. There could be one like kind of there.
I was thinking the same thing. Like one bar with then like a grand design spiral where they go all the way around.
Yeah, hard to tell. This is why crowdsourcing is great. If a lot of people look at the image, we get more opinions and people, more eyes on something is better. What are we going to go with? Anybody voting in the chat?
I'm voting for weak bar.
Fair enough. Is there any sign of a spiral arm pattern?
Wish it was a meh option.
I'll put it in for yes. I'm feeling medium for this one. What about you guys?
I'm feeling medium.
Yeah. 2?
2.
Yep. I appreciate the can't tell one because it's got a little question mark, which I sympathize with strongly. For my senior thesis, I checked out a book called What Are Gamma Ray Bursts because that was on gamma ray bursts, and it was a great book. It had a cover. It was a wonderfully written book, but the cover was just green background with a big purple question mark on it, and I appreciated that. Okay, so we can see the central bulge. Oh yeah, we talked a little bit about this. There is nearly always a central bulge in a spiral galaxy, which is usually where the oldest stars live, and it's where our supermassive black hole lives. Small?
Yeah.
I'm not seeing anything too disturbed. What about you guys?
Relatively complacent galaxy.
Yeah. And it doesn't seem all that unusual to me.
Where the menagerie in this one?
Well, then we've got pictures like this, which are just, this is another example of why computers have some trouble because a low quality image like this is a lot easier to look at with a human eye. Yeah, we can do 1 or 2 more of these, I think, and call it a night. All right, this one is smooth. I'm hoping we get a cool one. Oh, maybe we switch tutorial. Nah. We're gonna call it round or in between.
I think it's kind of elliptical.
Yeah. This
It's
one?
kind of it's probably an elliptical galaxy, but it looks like an ellipse. That's what I'm trying to say.
I've told you about my students who said that it was the shape of an ellipsis, right? Yeah, that's some very well-meaning but slightly confused people turn in assignments that said orbits, these orbit in the shape of an ellipsis, which is a delightful image of an orbit that occurs at 3 discrete points. Okay, I'm gonna call this one undisturbed. Not all that irregular. Well, shoot, I don't know what to do with that. Yeah, some of these are a bit of a trick.
It's a gray fuzz.
Yeah.
This is kind of a thing that I've discovered as I've gotten more into astronomy. Not all the pictures are as pretty as the ones that come out of Hubble. Quite a few of them are just, you're looking at little dots on a screen.
Yeah. When you get really far, when you get really dim, stuff just gets out of focus real quick. Imagine, I mean, I bet everybody here has at least at some point thought about trying to take a photograph at night. It's the problem with space, it's always night. Okay, are we gonna go through with this one?
We've talked about it. I feel we owe the people one more galaxy.
All right, fair enough.
I think it's got a little feature to it, a little something, something.
Yeah, there's something going on there. We can call it a feature. We can say it has features. I don't think it's an edge on disk, though. An edge on disk would be much longer.
Mm-hmm. And if we're wrong, the masses will let us know.
Yes. That said, there's definitely not a bar. A galaxy walks into a bar.
Oh, we're done talking about mergers.
Okay, I would say I don't see any spiral arms here. There might be a bulge, but you can see it's a little bit lighter right there.
I definitely think there's at least a small one.
Yeah. It could be a little bit disturbed. It's definitely uneven.
Yeah, maybe you could put minor.
I'll put in minor disturbance. It's possible something disrupted it. You never know. Galaxies like to interact with each other. But probably not that many interesting features. All right, well, I think that's enough for tonight if you guys aren't.
Yeah. Mm-hmm. And Zooniverse will always be there. So if you guys feel like classifying more galaxies, you have any free time, always hit up Zooniverse. They always have a ton of fun projects on there.
Oh yeah, I used to use that when I was doing 8-hour days of research. I would take a break, do a few on Zooniverse, and then go back to my work. You can just take a few minutes, do a couple, takes your mind off something, and it's a lot of fun. You could also do ones completely unrelated. I'm an astrophysicist. There's ones where you can classify kelp.
Oh, or it's a type of lizard, and you can find them via satellite images on Zooniverse.
That one's fun.
Fascinating. The Kelp Islands one are great, but personally, I go a little insane when I'm looking at kelp for that long.
Yeah, so you can always access Zooniverse, be part of crowdsourcing, be part of citizen science. It's a lot of fun. Okay.
All right.
Do we have anything else?
No, I don't think so.
Mm-hmm.
All right. Well, thanks everybody for tuning in. It's been great answering your questions.
Great. Thank you. Bye.
Thanks everybody. Bye.
Ciao.